Alrighty, guys. So we're gonna try this out. Hopefully this works. If it doesn't, please email me as soon as you kind of are saying, "Hey, this isn't working. Something's not going on. The audio's terrible." I'll try to check it and rewatch it on my own, but always let me know if something's not working when we're doing something weird like this. So let's jump in. Section 3.3. This is a really kind of important section. It's about the differentiation rules. So what you should have gleaned from the material from 3.1 and 3.2 is this idea of a derivative. And the biggest idea of a derivative and kind of the biggest takeaway that you should have is that there's this derivative function, which we say f prime of x, right? And so this is the derivative of the function f of x. And f prime of x is the limit. And there was two different definitions we used. We used a different quotient where we had the derivative at a point, like say f prime of a, and then we used the limit as x approached a of f of x minus f of a over x minus a, and that's a great one, especially when we're dealing with finding the derivative just of a single point. But when we're finding generic derivative functions like this using limits, the better version to use, typically the one that will allow us to kind of more easily evaluate the limits, is the one where we have the limit as h goes to 0 of f of x plus h minus f of x over h. Okay. And so what's kind of nice about this is f prime of a is the slope of the tangent line, or I'm going to say slash, is the instantaneous rate of change of the function f at a. So this is what we should understand, right? So these derivative functions tell us the instantaneous rate of a change. If we can get a nice formula for it, right? I think one of the ones we did last class was things like, so if we look at an example, say find f prime of x for f of x equals x squared minus 3x plus 6. Say that. All right, let's do this real quick. So then what we end up with is, so we go, okay, well, the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, and so what we're really kind of keen on here, and so this is something that I had gotten some questions about, was, well, when do I use the this version versus when I use the f of x minus f of a over x minus a? And it really comes down to when we're trying to find at a single point, the x minus a version works well, but it doesn't work well here because we would have an unknown value of x and we would have an unknown value of a, and they're moving to each other. This way we kind of have this, it's just a little bit easier to work with. So make this more proper. F prime of x equals that. And so then this, right, we're going to substitute in what we know. So I know that f of x plus h is x plus h squared minus 3 times x plus h plus 6. We have minus f of x, which is x squared minus 3x plus 6. And all that is over h. So this process of using these limits to find these derivatives is really a kind of time-consuming process. And it is a very algebra-intensive process, as you've probably seen from doing the problems, and you're seeing from this example here. And so one of the really cool things about what we're going to do today is we're actually going to figure out ways to simplify this process. We're going to see kind of how these patterns play out. So in our numerator, x plus h squared ends up giving me x squared plus 2xh plus h squared. Then we have minus 3x minus 3h plus 6. And so that was just kind of getting rid of parentheses from this first piece here, the f of x plus h piece. And I'm going to distribute this negative in, and so we get minus x squared plus 3x minus 6. And all that is still over h. Okay. So we're still evaluating our limit as h goes to 0. Now I'm going to use red here, and I'm going to cancel things out that we can, right? So I have a minus 3x there, and I have a plus 3x there, so those are gone. I have a plus 6 and a minus 6, so those are gone. I have an x squared and a minus x squared, so those are gone. So what I'm left with is 2xh plus h squared minus 3h all over h. Now we can't evaluate this limit by direct substitution because we end up with the 0 over 0 situation. So we need to change this in such a way that we have something that we can substitute in. And the easiest way to do that is factoring and canceling. So we're going to still take our limit as h goes to 0. I'm going to factor in h out of the numerator, leaving me with a 2x plus h minus 3. Okay. Minus 3 all over h. Using red again to cancel, right? Those two h's cancel each other out. And so we end up with the limit as h approaches 0 of 2x plus h minus 3. By direct substitution, this just gives me the equation 2x minus 3. So all of that work to tell me that f prime of x equals 2x minus 3. This is hoping, let's say when f of x equals x squared minus 3x plus 6. I believe that was right. Yeah, minus 3x plus 6. So what this tells me is that, so let's say simply like f prime of 2, right? That's just 2 times 2 minus 3. 2 times 2 is 4. Minus 3 gives me 1. So this tells me that the instantaneous rate of change of f at x equals 2 is 1. And so that's one of the main things we use derivatives for. We'll definitely develop some other uses for them. One of the really cool things is we can actually use derivatives to get a sense of the graph of other functions, of the kind of the antiderivative function, the step up. So, but what I want to talk about is ways that we can simplify this problem. Not just because I am a mathematical person and a math teacher, but because I know the derivative rules. Finding the derivative of this function when we get done with this section, and when you're done with the homework and everything like that, and especially once we get down to the test, this problem here is going to be one of the easiest problems you do. This problem here should take you no more than about 30 seconds. You should easily be able to look at this, right? Or if we wanted and say, from here we could say that f prime of x is 2x minus 3. Or say, if we have something like g of x equals 3x cubed plus 4x squared minus 8x plus 13, right? Doing this using the method that we've done, using these limits, would be crazy amounts of algebra. Imagine, I mean, just with squaring, right? We'd have, the x plus h squared component, but now we'd have an x plus h cubed component, and that just gets really crazy, really messy, really quick. But using derivative rules, which is what we're going to learn in this section, g prime is 9x squared plus 8x minus 8. And it's that easy. Really is that quick and easy that we're going to be able to do this. And we'll revisit this problem here. I'll try to remember this exact one to revisit later on in this section. So let's get going into 3.3. So this is so far we've just kind of rehashed 3.2 a little bit. And so if you're reading through 3.3 and you're looking through that, there's some kind of rules, and I want to just kind of list some of these out and then kind of talk about them, kind of work with them. A really simple one, and this might be kind of obvious when you actually think about it, think about what this is. If we say, let's see, be a constant real number, not n, and that f of x equals c, then f prime of x equals 0. Okay, there's a typo in the, I'm not sure if it's in there still in the digital copy. In a print copy that I have from last year, there's a typo in this where it says then f prime of c equals 0. That's not what's true. F prime of x equals 0. So this is using this f of x function here. So we get this. Now, one thing that I did not introduce in the last section, and that's mostly because things just were a little quick and hectic and I wanted to just push some stuff out there. There's another notation for derivatives. So we know, I'm going to put a little star next to this. We know that f prime of x is the derivative of f of x. Okay, and that works great for functions, but if we don't have functions, sometimes we just have an expression, right? We could actually say, we could use this notation, d dx, and so we'd say d dx of, and I'm just going to put exp. Okay, this is the derivative of the expression, which that is our exp, with respect to x. So that's that dx part. The reason why we want this kind of this idea of the derivative with respect to x is we're going to get some times later on where we're going to have functions maybe with multiple variables, especially if you continue on in calculus. And with that, you will end up with some versions like you'd say, d dx, d dy, and kind of the order of those differentiates kind of what we do, kind of how we interpret those and how we work with those. If I had something like, say, dy dx, this is the derivative of y with respect to x. Okay, and lastly, if we have something like df dx, well, this is just simply f prime of x. Right? Same thing that we've been doing. Okay. All right. So I have hit on a few things that I wanted to talk about. And the reason I brought up this denotation is because, so we know from up there what we call the constant rule. We'll actually give this name. Constant rule. We know if f of x equals c, then f prime of x equals 0. Similarly, d dx of c equals 0. Okay, and we'll use parentheses here just to of z equals 0. So this is just saying the derivative of a constant is 0. And that makes sense, right? So this is all just saying derivative of a constant is 0. And that makes sense because a constant function is horizontal and has no slope, right? Ooh, whoops. Constant function is a horizontal line, not line, line, and has no slope. Right? Has no slope or slope of 0. And so it makes sense that the derivative of that would be 0 as well. There's no change happening. Whether it's instant or over a long period of time, there's no change going on. So I'm going to end this video here. I'm going to kind of chunk up this lecture video so that way if you guys are watching or anything like that on separate devices or whatever you're doing, you can have this chunked up. And yeah, so this is the end of part 1. Continue on for the next awesome rule that we're going to use. And this rule that we're going to cover next is one of the most powerful rules, and that will cover what we just did with that g of x function, what I did. So see you in part 2.